All right, welcome back, everyone. So today we're going to talk about IV characteristics of linear networks. So we've introduced IV characteristics for elements, and now we're going to look at it for a network of elements and what that looks like and how we can use that to look at what's going to happen when you connect networks together. So the first thing I kind of want to point out is that we've created a box and called it a linear network. And so inside here are going to be sources like voltage and current sources and resistors and things like that. And then on this side we have another linear network that we're calling a load. Now this could also have sources in it, but for our purposes we're generally just going to look at this as being a bunch of resistors. Now the only difference between these two networks is the direction that we're choosing the current to go as we define it. And so we have two terminals, or we'll call it a port. And so on these two terminals, the voltage across it is defined as V. And since we have the current leaving out the positive terminal, that kind of defines this as a source network. And in this one, it's the same thing, except we have the current I entering the positive terminal. And so this would define that as a load network. So we're going to create a source IV characteristic and a load IV characteristic. And so the IV characteristic is determining all the combinations of V's and I's that could exist on this terminal based on what's inside the network. And the same thing for the load network. And so by convention, we see that I leaves the positive terminal for sources, and that's what we have here. And then by convention, I enters the positive terminal of loads, and so that's why we have that there. So this is kind of what we were dealing with before. Now we're going to expand it into a bigger network. When defining the IV characteristic of a linear network, we want to decide if we're going to treat it as a source or a load, and that will allow us to kind of define if we're having I going out or into the positive terminal of that network. So how do we find the IV characteristic? So since these are linear networks, all the IV characteristics are going to look like lines and on the IV graph. And so if we write the equation slope-intercept form of the line, y equals mx plus b, we're not dealing with y's and x's here. We're dealing with currents on the y-axis and voltages on the x-axis. So our general form for the IV characteristic equation is going to look like I equals mv plus b. So we have to find out what M is, and we have to find out what B is. And so this kind of procedure that we're going to go through is going to help us find those two things. So to define a line, any line is defined by two known points. So we have to choose 2 points that we can plug into here. If we can find 2 different points of I and V, then it'll allow us to solve for the 2 unknowns M and B. And that's what we're going to do. Remember, the IV characteristic is every possible combination of VI for anything that's connected between the two terminals of these networks. So I'm starting out with a general kind of introduction to this, and then we're going to look at an example. So first we're going to talk about the source. So we're having the current, and both of these are leaving the positive terminal. So which 2 points are we going to find? And so an easy set of points to find are called the open circuit and the short circuit coordinates here. So we'll find 2 particular VI coordinates, one for an open circuit and one for a short circuit. And so to do this, we're going to take our network, whatever it is, and we're going to leave the terminals unconnected, making that an open circuit. They're not connected to each other. And with them unconnected, we're going to figure out what the current coming out of that positive terminal is and what the voltage across the 2 terminals is. The second thing we're going to do is take a short circuit, and we're going to make a short circuit by just connecting the 2 terminals together. That's what's called a short circuit. And then we're going to figure out what the current coming out of the network is, and we're going to find the voltage across the 2 terminals with it being shorted. Now, if you were going to try to do this with a real circuit, you could use a multimeter, a voltmeter, and an ammeter, and you could actually just measure the open circuit voltage and then short it and measure the short circuit current, and then we can get those terms that we need right there. So let's just point out a few things that we can notice just by inspection. First, I just wanted to define VOC and IOC is the open circuit voltage and current, and ISC and VSC are the short circuit current and voltage. And so by inspection, you can see that IOC and VSC are both 0. So let's take a look at that. If there's no path because of this open out of this node here, so this ends, so the IOC must be 0, so there's no path for it the current to flow. So that makes IOC 0. And on the short circuit one, since this is the same node, so we've connected the terminals together, the difference between the positive and negative side of this node is 0, so they're both the same. So that makes the short circuit voltage 0. So those are important points. We can see that in our equation, if we have I is equal to M times V plus B, when we have the open circuit voltage is 0, that means that the X is 0. I'm sorry, when we have the open circuit current is 0, that means the Y value is 0. So what we're finding here is that the open circuit voltage is going to be the X-intercept. What is the voltage when the Y value is 0? Right? And then the same thing for when we have the short circuit voltage is 0. So if the short circuit voltage right here is the X part of the graph, that's when X is 0, and that is what we call the Y-intercept. So when X is 0, what is the short circuit current? So we can see that the short circuit current is the Y-intercept of our graph, and the open circuit voltage is the X-intercept of our graph, and we'll look at that a little bit more as we go along. So I'm just going to plug these 2 points in a general sense, if we were solving for these, and if we were going to use the equation of the line on our characteristic equation for these 2 situations. Remember, we're trying to find that line, so we're using 2 points and to be able to define that line. So let's just plug in here. So Y is IOC, X is VOC from this first circuit, and so writing that out and leaving it in general terms, I know that the open circuit current is 0, so I plug in 0, and I'm just rearranging this to solve for the open circuit voltage, and I get it as negative B over M. Okay, we're just going to stop there for a second and go over to the other circuit. And so in this case, I have ISC equals M times VSC plus B. We know that the short circuit voltage is 0, so I can plug in 0, which removes that term. And I get that the short circuit current is just equal to B, which we said is the Y-intercept, so the short circuit current is the Y-intercept. And we're looking for B, so I'm just going to rearrange that. So if I know the short circuit current, if I can measure that or solve for that, then I know the intercept for our characteristic equation, so B. Then I'm going to plug back in here for B as ISC, and so I rearrange this equation, solve for M as negative B over VOC, plug in for ISC, and then I get negative ISC over VOC. So now I've solved, in a general sense, for the slope of our characteristic equation, or our IV characteristic, and the slope is going to be the negative of the short circuit current over the open circuit voltage. So using these 2 solutions for M and B and plugging that back into the equation, I have Y equals MX plus B, and then I've substituted Y is I. M from the last page is negative short circuit current over open circuit voltage multiplied by my X variable, which is V, and adding to the intercept, which was the short circuit current. And so we can see that we can find the characteristic equation of the network if we know these 2 things, the short circuit current and the open circuit voltage. And so like I said, if we were going to measure this, we can find those 2 things with a multimeter, an ammeter, and a voltmeter. But if we were going to solve it via circuit analysis, which we're going to do here, we have to find those 2 terms, and then we can write this equation. And so this is the IV characteristic of a source in terms of a source network in terms of ISC and VOC. So what is this going to look like on a IV graph? And so this is kind of what's going to happen here. So I know that the short circuit current was the Y-intercept, and the open circuit voltage is the X-intercept. So there's going to be some current here that has some positive value, some voltage that has some positive value that will lie on the axes, and then that defines a line. So we're using these 2 points to define this line here. And so this is the IV characteristic of the source network. And you can see that the intercept is ISC right there, the short circuit current. And then what about the slope? Now the slope, if you look at the slope of this line, has a negative slope, so we have a negative value there. This change in Y is actually from ISC to 0, so that's negative ISC. And this change in X is from 0 to VOC, so that's a positive VOC. And so our slope is negative ISC over VOC, and that's indeed what's in our general solution as well. So generally, we are only concerned with the first quadrant where both the I's and V's are positive. Notice if we go along that line further, now we have negative currents, and so now it's not really acting like a source anymore. And so over here we have negative voltages, so again, it's not acting as a source network anymore. So for our source network, we're really looking at it operating in that first quadrant. This is called a load line, and it's called a load line because if we put any load onto that network, onto those two terminals, anything connected to those two terminals will result in a point somewhere along this line. And if we're concerned only with the first quadrant, we'll get a point somewhere in here. And when we find that point, when we attach that load, it specifies that point, and that becomes our operating point for the circuit. And so let's go ahead and take a look at the load network. So here is our load network from our first page. We have the current now entering the positive terminal, defining this as a load network. And so generally, we're going to be looking at an equivalent resistance inside that load network. So we have to find REQ from whatever sort of resistances are in there and whatever configuration they have. If we notice this, we can't actually use open circuit and short circuit analysis like we did for the sources, because if we open this circuit and we see that there is no current flowing in, by Ohm's law here, if there's no current flowing in, there's no voltage drop, and so that would mean that this is the point 0, 0. If we short circuit and said that there's no voltage drop across this resistor, by Ohm's law, there's also no current flowing through it, and so we get the point 0, 0 again. And so VOC, IOC, and VSC, IOC are both going to be 0, 0, so they only give us one of the points. That's not enough for us to draw the line. They give us this point right here on the characteristic curve, characteristic graph. And so we're going to use Ohm's law because we know that V, I, and R, we already have this relationship. And actually, if you look at this, how I've written it, it's I is equal to a term multiplied by V, and then there's no intercept because the intercept goes through the origin. This is written in the form of an IV characteristic already. So we have our slope is just 1 over the equivalent resistance. And so we can use Ohm's law to figure out the characteristic IV characteristic for a simple resistive network. And this has no sources in it. So this is what it looks like when there's no sources. Again, here's just a reiteration of the two open circuit and current and voltage and short circuit current and voltage. They both have the value 0, 0 for this network. And so we get that point only, and we use Ohm's law to get the rest of that. So then we talk about an operating point. So I have any source network and I have any load network. And the idea is that when I connect them together, they have to have the same voltage across these two nodes, and they have to have the same current flowing through these two terminals. And so that's kind of the idea of using this analysis to find the operating point. If I know the two characteristic IV characteristics for the two networks, when I connect them together, I can solve for where they're going to operate. And so here's an example in a general sense. So first I have my load line coming across right here. This is from the source network. And then I have my resistive line, IV characteristic that we got from Ohm's law, and that's the load network. And so where they intersect is going to be the operating point, giving me a particular V and a particular I that will be manifested at these nodes right here as they're connected together. So just some notes. When we connect the two networks together, the particular VI that results is called the operating point. It is the intersection of the two IV characteristics on the graph. It is also the simultaneous solution of the two IV characteristic equations. So this characteristic equation for the load and then the previous one that we found for the source. So I'm going to go through an example now of how we find the IV characteristic if we have a given source and load network. So here's my example source network. So 50 ohm voltage source, we have a 10 ohms in series with it, 5 ohms here coming down to the bottom terminal, 4 ohms, 20 ohms, and a 2 amp current source. And so this is a moderately complex source network, and we're looking at these two terminals. This is what we're interested in terms of finding the IV characteristic at these two terminals, or this port. So how do you do that? Well, you use your favorite method to solve the circuit for I and V, and we do that 2 times, one for an open circuit on these terminals and one for a short circuit on these terminals. So I want to start with the open circuit. So I'm going to use node voltage method. I've defined A here as my ground node, my reference node, and I marked up that bottom node. It goes all the way across. We have B, C, D, and E. So even though this isn't connected to anything further, it still is a node in our circuit, and so we have to define it that way. And we're looking for IOC and VOC here for the open circuit. Okay, so I'm going to start right here and look at defining VOC and IOC in terms of the rest of the circuit. So VOC is the voltage at E minus the voltage at A. So I can define that as VE minus VA. And IOC flowing this way out of this terminal here is the same current by Kirchhoff's laws that's flowing through this 20 ohm resistor. And so I'm going to define it as VD minus VE over that 20 ohms. And so we have definitions for VOC and IOC ready to go. You might remember that the open circuit current is 0. So I actually already know that this is going to be 0, but I just want to go through the whole solution so that you can see kind of how that comes about. But if it's not connected to anything, there's going to be no current flowing through this 20 ohms and no current flowing out. So we already know that's 0. And we're really interested in finding what this open circuit voltage is. So next step is to write my KCL for the unknown nodes. And so solve for the easy ones for my node voltages. So 0 volts for VA, 50 volts for VB. Now I have 3 unknown nodes. Writing for C, I can write my node equation. Writing for D, I write my node equation. Writing for E, I write my node equation. And I solve these simultaneously. And so I just plugged it into online solver of 3 simultaneous equations, linear equations. And we get these values. VC is 23.3, VD is 31.3, and VE is 31.3. So these 2 nodes have the same voltage of 31.3. So now I can go back and plug into my original equations, what I'm trying to find. So VOC is VE minus VA is 31.3 minus 0, or 31.3. So this is a really important piece because that goes into our equation for the characteristic equation for the source. IOC is VD minus VE over 20, but VD and E are both the same value, so we get 0 ohms. And again, we already knew this because that was one of the definitions we arrived at in the very beginning. Second part, using the short circuit to get our second point. And so this time, I do the same thing. I've defined all my nodes, and I've connected the terminals together, and that's our short circuit. And so what this does is extends node A all the way around to both of the terminals, okay? So then let's find out our values that we're looking for. So we want to find the short circuit voltage and the short circuit current, and we can see short circuit voltage is VA minus VA, but that's equal to 0. We already knew that. We are not as much interested in the short circuit voltage because of this. It's given us our 0 point for the voltage, but we want to find the short circuit current. This short circuit current is the current that goes through 20 ohm resistor, and so we have VD minus VA over 20. So easy ones, 0 volts for the ground node, 50 volts for B. This time we only have 2 more nodes, C and D. I write out my node equations for them and solve. Then I get VC is 19.5 volts and VD is 22.9 volts. Plug those back into my original equations, and I already knew that the short circuit voltage was 0. Plugging into ISC is VD minus VA over 20, or 22.9 over 20 gives us 1.145 amps. So that is our short circuit current. That is also our y-intercept on our graph. So when we put our characteristic together, we can use that as the y-intercept. So this is the equation we came up with for the general form for the IV characteristic, using the short circuit current and the open circuit voltage. And we just found those 2 values. The short circuit current was 1.145, the open circuit voltage is 31.3. And so I can write them in and plug them in here. So ISC over VOC, and then the negative of that gives us a value of negative 0.0366 Siemens. So this is a amps over volts, and that's conductance value, so that's a Siemens. And so then I can plug in with our real values. For this specific for this specific source network, we have I is equal to negative 0.0366 Siemens times the voltage plus 1.145 amps. So this is our source network characteristic equation. If I wanted to graph that, I know what it looks like generally. It has this line that goes across the first quadrant like that. We have the short circuit current as our y-intercept, 1.145. The open circuit voltage is our x-intercept. It's 31.3 volts, and those are the two values we solved for, and so that gives us our line. The slope here then is negative 0.0366 Siemens. So there it is, we found it. So the next thing that I want to do is do an example for a load network. And so here we are finding the load IV characteristic for something that has no sources. So we wanted to find REQ first, and then use the characteristic as Ohm's law. So here's a load network that I created. We have 6 ohms in series with 2 parallel 10 ohm resistors. And we're drawing the I arrow into this network since it is a load network, and we have our voltage that's across those 2 terminals. So this was the box in the first picture, right? So first thing we need to do is make all these resistors into one resistor, REQ. So I'm gonna combine the 2 parallel ones. Call it RA is 10 parallel 10. So 10 times 10 over 10 plus 10 gives me 5 ohms. And then that 5 ohms is gonna be added in series with that 6 ohms. So we have an equivalent resistance of 11 ohms. And so here we have our equivalent resistance for our load network, and the value for REQ is 11 ohms. So now I can just use Ohm's law. I is 1 over REQ times the voltage, and so plugging in 1 over 11, that gives us our equivalent conductance, if you will, and it has a value of 0.0909 Siemens. So I is equal to 0.0909 times V, and that is our load network characteristic equation. On an IV graph, it has 1 point, that's the origin, because it has no y-intercept, and then it has a line that has a positive slope of 0.0909 Siemens. And there it is. So that's not too hard to go ahead and figure that out. Lastly, we're going to find the operating point. So we're going to take our source network and we're going to connect it to our load network, and we want to find out at the point of connection what is the voltage across those 2 terminals and what is the current that flows from the source to the load network. And so to do that, we can put our 2 graphs onto an IV graph, our 2 curves. And so we have our our source network that we defined on the last page, and we have the load line, the load characteristic equation that we created just now above, and I can find the intercept point. And so you could do that on a graphing calculator or something like that, or else you can just go ahead and set the equations equal to each other and solve for those voltages. So we know when they intersect, the 2 currents are going to be the same, and since we're writing them in terms of the current on the left side of the equation and isolated, I just like to set them equal to each other. So from the previous page, I was equal to negative 0.0366 volts plus 1.145, and times V plus 1.145. And on this page, we see I is equal to 0.0909 times V. So setting them equal to each other like this, just solving with algebra, we find that V is 8.98 volts. Then I can sub back in for I, and so I'm going to use the one on this page. I is 0.0909 times 8.98 volts, and we get an I of 0.816 amps. So our operating point at that location, when we connect these 2 together, is determined to be 8.98 volts and 0.816 amps. And that's how we use the IV characteristics of these source and load networks to figure out what's going to happen when we connect them together. Just one last picture here. This is kind of going back to a general look. So we attached our source linear network and our load linear network, and when we connected those 2 together, this is what we see at the connection point. 8.98 volts across the 2 terminals and 0.816 amps going through them. Thanks a lot for watching.